Welcome to the University of Lincoln and the School of Pharmacy and this bite-sized lecture on partition coefficients. Now in this lecture we're going to have a look at the way in which drugs partition between water-loving and lipid-loving environments. These properties are very important in terms of the drug's absorption and distribution, and the information is also used in drug formulation. Now this lecture does make some assumptions. It assumes that you know the structure of a cell membrane. It assumes that you understand exponents and logarithms. And it assumes at least some familiarity with the concepts of acids and bases, the acid dissociation constant, or pKa, and pH. About 80% of the drugs on the market are taken orally. This is because it's a convenient and non-invasive route of administration. However, simply by swallowing a drug, you cannot assume that that drug will then enter the bloodstream. It has to pass through a number of biological membranes in order to do this. So the drug is taken by the oral route and it goes into the gastrointestinal tract. From there it is absorbed into the bloodstream, and from the bloodstream it will go to the site of action. For the drug to be absorbed into the bloodstream through the gastrointestinal tract, it has to pass through cell membranes. Cell membranes are made of a phospholipid bilayer, and they're very often drawn like this, with a hydrophilic head and a lipophilic tail. For the drug to pass through that membrane, it has to have the right balance of water and lipid solubility. It's very important to understand that we are talking here about passive diffusion. The drug is going from a region of high concentration, such as the lumen of the GI tract, through the membrane into a region of low drug concentration, such as the bloodstream. No energy is being expended. There are other methods by which drugs can pass through membranes, such as membrane transporters, which typically involve ATP and energy. We are not concerned with those mechanisms here. We are dealing entirely with passive diffusion. Now there are two questions that we need to get answers to. Firstly, we need to know how we measure the water and lipid solubility of a drug. And then we need to understand what the right balance is between the water and lipid solubility in order for that drug to go through the cell membrane by passive diffusion. Now that is the subject of this bite-sized lecture on the partition coefficient. Let's look at the first question, which is how to measure the relative water and lipid solubility. It can be done experimentally, very simply, using a separating funnel. Into the funnel you place a quantity of water and a quantity of octanol. The octanol floats on top of the water, forming two phases. The drug of interest is then placed into the funnel, it is shaken, and the drug will partition between the octanol and the water. After some period of time, the octanol and water will separate out into the two phases, and you can then measure the amount of drug in the octanol and the amount of drug in the water. In the example here, I've put a little bit of blue dye into the separating funnel so you can see the partition of the blue colour between the octanol and the water. And I think you can see that the blue has gone a little bit more into the octanol than the water phase. Now why do we use octanol? Well, octanol has very similar properties to the lipid phase of the membrane. So in other words, it's just a good model. Okay, so we have now got some measurement of the way in which the drug partitions between the octanol and water layers. That ratio of water to octanol is known as the partition coefficient, or P. Let's look at an example here. Let's say that the drug partitions equally between the water and the octanol. Then obviously P is going to be 1. The trouble is that the value for P can be an extremely small value or an extremely large value. So under these circumstances, we often take the log of the number. So here we take the log to the base 10 of P, which gives us the log P. The log P is the log of the partition coefficient. Let me put up the equation for log P. Log P is the logarithm of the amount of drug in the octanol layer divided by the amount of drug in the water layer. Let's look at some more examples. We go back to the one that we just dealt with, where the drug partitions equally between the octanol and the water. We said that P equals 1. Well, the logarithm of 1 is 0, so the log P equals 0. If the drug partitions a million times more in the octanol phase, then P is 1 million, and the log of a million is 6, so log P is 6. If the drug partitions a million times more in water, then P is 1 times 10 to the minus 6, and the logarithm of 10 to the minus 6 is minus 6, so the log P is minus 6. Let's look at this diagrammatically. In the middle here we have a log P of 0, whereby the drug is partitioning equally between the water and the octanol. As the value for log P becomes more negative, so the drug is more hydrophilic. And as the log P for the drug becomes more positive, so the drug is more lipophilic. Now, as a general rule, if you have a log P between 0 and 3, it will have the right balance of hydrophilicity and lipophilicity in order for it to cross the cell membrane by passive diffusion. Now, this is not an absolute value. Drugs with log P's outside of 0 to 3 can still cross the membrane. It's just that these are the ideal conditions between 0 and 3. So, go back to our original questions. How is the water versus lipid solubility measured? And the answer is by the partition coefficient, or log P. What's the right balance of water to lipid solubility for that drug to go through the membrane by passive diffusion? And it's a log P somewhere between 0 and 3. This looks all very straightforward. Unfortunately, it's not quite that simple, and there are some other factors that we do have to consider. The log P is measured when the drug is completely unionized. What do we mean by this? Well, we need to look at this in a little bit more detail. You see, most drugs are either weak acids or weak bases. I've taken 2 drugs as an example here. Aspirin, which is a weak acid, and morphine, which is a weak base. Here are the structures of the aspirin and morphine. If we look at the dissociation equations, then we can take an acid, which is HA, and we put that into water, and it will form the hydroxonium ion, and then the anion of the acid. at the bottom of the slide, I've written it down again specifically for aspirin, and I've colour coded this so you can see how aspirin correlates with the general dissociation equation. Now, the extent to which that acid ionises is expressed by the acid dissociation constant, or the Ka. There is an equilibrium between the dissociated and the undissociated acid. Now I can put the general equation for Ka up here, very straightforward. The Ka is simply the dissociated or ionised form of the acid divided by the concentration of the undissociated or unionised form of the acid. And again, I've written it out underneath for aspirin as an example, just to try and make it clear. Now that's the Ka, but we don't use Ka that much. We use a different parameter called pKa. Now a lowercase p signifies a negative log. It's exactly the same, for example, with pH. pH is the negative log of the hydrogen ion concentration. So we use pKa, and you can find the dissociation constants, the pKa's, for a range of drugs. If you try putting pKa in the name of a drug into Google, you're quite likely to find a value. The pKa for aspirin is 3.38. Now, the proportion of ionised to unionised molecules in a solution depends upon two factors. It depends upon the pKa of the molecule. The pKa of the molecule is an intrinsic property of that molecule. And it also depends upon the pH of the solvent. And of course the pH can vary. pH is a variable. Let's go back to that dissociation equation again and look at this in a little more detail. Here we have on the left the undissociated acid. We have an equilibrium by the pKa, and on the right we have the dissociated or the ionised acid. Now the undissociated acid, that is going to partition between octanol and water. But the ionised form of the acid, the dissociated species, that is only going to partition into the water. It's charged, it will not go into the octanol, it will only go into the water. So the undissociated species that is partitioning between the octanol and the water, that is the LogP. The LogP is of the undissociated species. But what if we want to take into account the ionised form? Well, the overall partition coefficient, which includes the undissociated and the dissociated species, we call that the LogD. Now let's just plot this out, so just explain this in a little bit more depth. Here is a graph with pH on the x-axis and the percent of drug dissociated on the y-axis, and I've plotted it out for aspirin and for morphine. And you can see here for aspirin it is completely undissociated. It is 0% dissociation at a low or acidic pH, because aspirin is an acid. And for morphine it is completely undissociated at the high pH. So when we measure LogP, we measure the LogP of the undissociated form. So for aspirin we measure the LogP at low pH. And for morphine we measure the LogP for the undissociated form at high pH. Now the bit in the middle, the partition coefficient, when some portion of the drug is dissociated, that is the log D. So we go back to the original equation that I put up. Log P is log to the 10 of the amount of drug in octanol divided by the amount of drug in water. We need to correct that to the amount of drug in octanol divided by the amount of undissociated drug in water. And for log D, it's the amount of drug in the octanol divided by the amount of undissociated drug in water plus the amount of dissociated drug in water. It's the total amount in the water phase. Now log P is a measurement of the partition coefficient where all of the compound is unionized. The log D is the partition coefficient where some portion of the compound is ionized, but that is pH dependent. So it is very important that when you quote a log D, you must also quote the pH at which the log D was measured. And in this example, the log D was measured at physiological pH of 7.4. Okay, so log D is a property of the pKa and the log P of a compound. Both the pKa and the log P are intrinsic properties of that compound. And a variable, which is the pH. The pH can vary depending upon the environment. And if you use those three factors, pKa, log P and pH, you can then calculate the log D. The equations to calculate log D are shown here. They're slightly different for acids and bases. I won't read this out in full, but if you look at the exponent of the 10, for acids the exponent is pH minus pKa, and for bases the exponent is pKa minus pH. Very similar equations, but slightly different. So, if we know the pKa and we know the log P, in whatever in pHs of the environment, we can then calculate the log D. So let's plot it. Let's plot the log D against pH for aspirin and morphine. This is what it looks like. Now, log D is on the y-axis, and if you remember, the sweet spot for absorption is around is between 0 and 3. So that's just above the x-axis there. So the blue plot for aspirin, that is in that sweet spot in acidic conditions. And for morphine, it's just in the sweet spot, only barely, just in the sweet spot at basic pH. So that means that aspirin is absorbed by passive diffusion at acidic pH, such as in the stomach. And as aspirin passes down the GI tract, where the pH drops, so it becomes more difficult for it to be absorbed through the biological membrane. So this explains why aspirin is absorbed in the stomach. The opposite is true of morphine. In acidic conditions, the log D is very low. In stomach conditions, it's around -6. But in the lower part of the pH of the GI tract, where the pH starts to drop, morphine is then absorbed. But nevertheless, morphine is only poorly absorbed, and it's in the lower part of the GI tract. So this explains why the partition coefficient is important for understanding drug absorption. It tells you where that drug is likely to be absorbed and under what circumstances. Okay, last slide of this bite-sized lecture, we'll just summarise. Log P describes the partition coefficient of a compound when it is completely unionized. If you want a partition coefficient which takes some portion of the compound being ionized into consideration, you use the LogD, but when you quote the LogD, you must state at which pH it was measured. We can calculate the LogD mathematically, providing we know the LogP and the pKa of the compound, and of course the conditions of pH under which LogD is then quoted. The sweet spot for absorption through a biological membrane by passive diffusion for both LogP and LogD, it makes no difference, is between 0 and 3. And just once again, I will underline that we are talking here about passive absorption where no energy is expended. Thank you very much for listening, and I hope you enjoyed the lecture. Goodbye.